So there are several ways to assess slope stability. The simplest are empirical and analytical methods based on engineering experience. In some cases, an engineer can estimate the allowable slope angle using analogs and reference data. For example, for loose field soils, published guidelines define maximum unreinforced slopes. Typically, it's around 34 to 37 degrees for dry, dense sand. For rock masses, empirical criteria rely on mass classification systems. If the rock is strong and massive, meaning it has high RMR, steeper slopes can be used. If it's weak and fractured, the gentler angle is recommended. These empirical approaches are useful during preliminary design. They offer a quick grasp of conditions, but they don't account for all variables. So as a result, they're usually followed by more precise calculations that consider site-specific parameters. Still, such initial estimates help engineers make early decisions and prioritize areas for more detailed analysis. Limit equilibrium methods, or LEM, are the geotechnical engineer's primary tool for slope stability calculations. The concept involves assuming a potential slip surface, for example, circular arc in homogeneous soils, or planar surface along a weak layer of fracture in rock. These methods then calculate the balance of forces acting along the surface. Resistant forces like a mass of stable soil, shear strength, cohesion versus driving forces like weight of the unstable portion, water pressure, seismic forces, etc. Classical LEM techniques, such as those by Fillenius or Bishop, differ in mathematical assumption, but they arrive at the same goal, computing the factor of safety. For rock slopes, specialized schemes apply, like wedge failure or planar sliding analysis. In case of wedge failure, a block is bounded by two intersecting fractures, and in case of planar sliding, the mass slips along a single inclined plane, for example, weak bedding layer. And K-mine can automatically iterate through multiple possible slip surfaces to find the most critical one with the lowest safety factor. And this dramatically simplifies the engineer tasks, enabling rapid analysis of complex slopes, which includes multiple soil layers and water conditions. Another level of analysis involves numerical modeling using finite element or finite difference methods. Unlike limit equilibrium, which assumes a predefined failure surface, numerical methods simulate stress and deformation throughout the entire soil or rock mass. The finite element method, or FEM, is especially valuable for complex conditions such as nonlinear soil behavior, irregular slope geometries, or stage construction. FEM also divides the slope into a mesh of elements and solves equilibrium equations for each, producing detailed visualizations of stress distribution, displacement, and failure zones. Engineers can see not only the factor of safety, but also where plastic zones are forming, how much settlement will occur, and where tension cracks may develop. Such analysis is available in K-mine or other specialized packages like Plaxis, which integrates seamlessly with geological models. In addition to static calculations, specific external factors often need to be accounted for. In seismic regions, slope stability is evaluated under earthquake conditions using pseudostatic methods, typically by applying an equivalent horizontal acceleration. Rainfall or climate factors also play a role. Prolonged precipitation, for example, can saturate slopes and reduce soil strength, so analysis must include moisture sensitivity. Another important dimension is probabilistic analysis. Since soil properties are never known with absolute precision, engineers must ask, okay, so what if the soil is weaker or the load is higher than assumed? Probabilistic methods such as Monte Carlo simulations allow for input parameters variability and estimate probability of failure. If the likelihood of slope failure is significant, this indicates the need for additional reinforcement. While such advanced approaches are less common in everyday practice, interest in them is growing, especially for high risk or sensitive projects. The result of stability analysis is just not it's not just a number. It leads to practical recommendations. Based on the analysis, geotechnical engineers determine whether a slope is stable and under what conditions it might fail. If the safety factor is insufficient, stabilization measures are proposed, and that's something we'll cover next. But it's important to stress that any calculation result it must be interpreted critically. A model is a simplification of reality, even a good model. So, engineering judgment is essential. Comparing different approaches also adds confidence. For example, if both limit equilibrium and FEM produce similar safety factors, the results are likely reliable. But if they differ greatly, it's something might be wrong. So, in today's environment where powerful software is available, the real challenge is to framing the right problem and thoughtfully interpreting results. By combining various analysis methods and using monitoring data, engineers can achieve accurate assessments and develop targeted mitigation strategies.